So new section right here, we're going to do electrochemistry. And so when we look at electrochemistry, we're kind of thinking of the idea of the movement of electrons. Whenever these things are reacting, basically, yes, atoms combine, atoms make compounds, atoms make molecules, but at the very end of the day, the basis of chemistry is that atoms will gain, lose, or share electrons in order to basically become, I guess, more stable, but it's order basically because we have positive and negative charges attracting each other, and there's just a simply attraction of electrostatics, of positive and negative charges. So let's kind of go through this real quick. I take myself some copper chloride, okay? And we've done this experiment several times. I'm gonna take copper chloride, this is an ionic compound. I'm gonna put it into solution, and what I get is I get copper ions and chlorine ions floating around. And remember why? We have ourselves water. Water has a negative side and a positive side. So it has a partially positive and a partially negative side. And what ends up happening is that water, partially positive side, is going to go to the negative side of this compound. The water has a partially negative side, is going to go to the positive side of the compound. That's going to cause adhesions, but then the water is still attracted to all the other waters that are out there. And they're all moving around, and they cause dissociation. And so what we end up getting is they pull, the adhesion, cohesion. The adhesion to the copper chloride from the water, and the cohesion between the water and all the other waters, and the waters moving around cause them to break up and dissociate. So now we get a solution of copper 2 chloride. Okay, let's look at another solution over here. We're going to take ourselves aluminum. Now, let's theoretically think of what's going to happen here. Aluminum and copper 2 chloride can react. All right, so aluminum and copper 2 chloride can react. Now, back in the back in pre-AP chemistry days, you would look at this and go, oh, that's going to be a single replacement reaction. We'll come back to this. Let me erase this to keep it clean. This would be a single replacement reaction. And you'd be right. Yes, it's a single replacement reaction. But what's actually happening is that I'm going to introduce this metal to these ions in the same solution at the same time. So I have my container. I have my copper ions. Now I'm gonna let you know the chlorine ions are gonna be what we call spectators. They're not gonna do anything. They're just gonna sit there and hang out. So we have our copper ions, and I'm gonna put in there some aluminum ions. And we'll just make up multiples of these. And these are not ions yet, this is just a piece of aluminum. So it's aluminum, solid aluminum. Now, what's gonna happen? This aluminum here has its own electrons. This copper ion is, of course, a positively charged ion. And so this copper positively charged ion, positive charge, negative electrons, this copper ion has the actual ability to behave as a non-metal. It can actually gain electrons and go from being a copper positive 2 to a copper 0, to a piece of copper. All right, so what happens is if the copper positive 2's positive charge has what we call a strong enough reduction potential, a potential to get reduced. Now, what does that mean? Being reduced means it's going to go from a positive 2 charge to a 0 charge. But once again, it goes all the way back to the very beginning. Opposite charges attract. If the copper positive 2 charge is able to go ahead and pull the electrons away from the aluminum, then this copper positive 2 electrons plus copper positive 2 makes copper 0. What would then happen? Well, the aluminum is going to go from aluminum 0 to aluminum positive 3 plus 3 electrons. Now I know you're gonna look at it right now and go, wait, copper only took 2. Aluminum lost 3. How'd that happen? This half reaction right here, this is the half reaction. This is the half reaction right here of what's happening from the copper, just a single copper by itself. This is the half reaction that's happening from what's happening to a single aluminum by itself. But we know balancing is going to take place. We know that when we take aluminum plus copper 2 chloride, we're going to get ourselves aluminum chloride plus copper. And we go back through and we balance this, and we see, oh, we need 2 here, and we got 6 chlorines, so we need 6 chlorines here, which means I need 3 coppers here, and I need 2 aluminums here. Well, let's go back up here. I have 2 aluminums and 2 aluminum ions. That's gonna have lost 6 electrons. We go back up here and we see that we've got 3 coppers and 3 coppers, 3 copper ions and 3 copper solids. And once again, what do we have? We have ourselves 6 electrons here. Hey, there we go. So what we actually have is what we call a redox reaction, reduction oxidation. We're gonna have ourselves the copper having 3 copper ions. So these 3 copper ions that are over here gaining 6 electrons from 2 aluminums, and this is aluminum 0 charge. Aluminum 0, why 0? Because it has 13 protons, 13 electrons when it just sits by itself. That means it's 0. 2 aluminum metals losing 6 electrons, becoming 2 aluminum positive 3s. 2 aluminum positive 3s, 2 aluminum cations. We would say that this guy got reduced. A positive 2 to a 0. A 2 to a 0 is a reduction in quantity of the oxidation number. So it's a reduction. And then we say this guy has gotten oxidized. This guy has gotten oxidized. So we call this whole thing a redox reaction. A redox reaction, reduction, oxidation. There's a cute little mnemonic I think we talked about before in here, and that is oil rig, like an oil rig. Pumps oil. Oxidation, it loses electrons. Reduction, it gains electrons. Or Leo the cat, Leo goes grr. Lose electrons oxidize, gain electrons reduce. Whatever. I don't typically use those. Of course, I've been doing this for a long time. What I typically just look at and go, hey, the guy whose oxidation number is getting smaller, that's being reduced. The other one's being oxidized, therefore. So, what's at the end of the day, what's the deal? How does this thing come into play? Like, why do we care about this at all? We see there's an exchange of 6 electrons. So if I take a hunk of metal and put it in here directly, what we see is there's a direct exchange of electrons. The electrons are just going at the interface. Where they meet, they're going from the aluminum to the copper. What if we don't let them do that? What if we don't let them exchange electrons at their interface? What if we make them do a job first? What if we make them do a job first? That's what we're going to get to next.